All right, today is a whole lot of review of trigonometry, things that we should have learned in geometry last year. So the first one is the Pythagorean Theorem. Next, we'll learn about the two special right triangles, the 45-45-90 and the 30-60-90, and their properties again. And then we'll talk about right triangle trig, which you might remember as SOHCAHTOA. Okay, so all of that is in today's lesson. It's all review, so it is going to be a little bit fast and a lot of information. So if you do have access to a printer, printing out the sheet will save you a little bit of writing for sure. All right, so reviewing Pythagorean Theorem. Pythagorean Theorem says if I have a right triangle, meaning we have a 190-degree angle, that the two sides next to my right angle are called our legs. Okay, and the Pythagorean theorem, these are not necessarily equal, sorry, I was just marking them. But it says that the sum of the squares of the two legs equals the square of the hypotenuse, which is always the longest side in a right triangle. Okay, so the hypotenuse is always kind of opposite our 90-degree angle. And we know, of course, a squared plus b squared equals c squared, where a and b are interchangeable, but the hypotenuse has to be c. Okay, so if we use that on our two special right triangles here. So our first one, our 45-45-90, we have two equal sides. The legs here are equal. Okay, so knowing that, if I call one of them x, we can call the other length x because they're the same. And if we use Pythagorean theorem, a squared plus b squared equals c squared, we can find a property that will always be true for the hypotenuse. So let's check that out. X squared plus x squared, this is our a squared plus b squared, equals our unknown length here, c squared. So let's say we're going to try to solve for c to find what this length would equal. So 1x squared plus another x squared makes 2x squareds. Next, I would need to square root both sides. And normally, of course, we would put plus or minus here for an even-numbered root. But because c is a length, and lengths can never be negative, we're only going to use the positive case. Okay, so those cancel out. And we get c equals the square root of 2 times the square root of x squared. Or the square root of 2x squared, of course, but you can separate them as individual radicals. That's one of our properties of radicals. They separate over multiplication and division. Anyway, so whether you separate them or not, when we simplify this, we have a pair of x's, which means we get to take an x out of our radical. So you can either think of the square root and square here cancel, or that we can take an x out of our radical. Either way, we end up with x times the square root of 2 is the length of c, the hypotenuse. So if this side length is x and this side length is x, the hypotenuse will always be x times the square root of 2. So for instance, if I said this is 5 and this is 5, this would be 5 times the square root of 2, right? It's nice, easy ratios to follow. Okay, our next one is called the 30-60-90 right, special right triangle. And this one actually starts from, we started with a model for it. If you start with an equiangular and equilateral triangle, where all the sides are the same and all the angles are 60 degrees, 60, 60, and the top is 60 as well. And you draw in an altitude, which makes a right angle from one of the vertices with the opposite side. Well, that ends up bisecting the angle up here, cutting it into half, and this becomes a 30-degree angle. Not only does it bisect that angle, it actually bisects this side. So in fact, this side length ends up being half of this length, but remember, all three sides were initially equal. So what that means is this length is kind of half of this side length. If we're just looking at this right triangle in here, this 30, 60, 90, and that's where this comes from. It's actually half of this equilateral triangle. So we get this ratio that this shorter side, because again, this kind of comes from this equilateral triangle where this length, and this length were equal, but this side got cut in half. Okay, so anyway, so if we call this length x, the hypotenuse will be twice x. That is something that's always true for this triangle. Now again, because we know something about two sides, relating them to the same value x, we can find a value that's always true for this other side. Okay, so in this case, this would be my hypotenuse, or c in the Pythagorean theorem. So let's call this a. We're going to say a squared plus x squared equals the hypotenuse 2x squared. Well, 2x times 2x is 4x squared. And if we move this x squared over, well, that's 1 less x squared. So now we have 3x squared. And like we did before, we're going to take the square root. Since a is a length, we only want the positive value here. And just like before, we're going to be able to take an x out of our radical because it's x squared. So this simplifies as x times the square root of 3. So this missing length up here can be filled in as x times the square root of 3. So if this length is 4, okay, this is the smaller length, we call this the shorter leg, because in this triangle the legs are different lengths. We call this the short leg, this is referred to as the longer leg, and this is the hypotenuse. So the shorter leg is 4, the hypotenuse will be twice as big, 2 times 4, or 8, and the longer leg would be 8 times the square root of 3. So it's just x, the shorter leg, times the square root of 3. And so this kind of shortcut is a very fast way to find some missing lengths in special right triangles. If you have a 45, 45, 90 or 30, 60, 90, you don't necessarily have to do the full Pythagorean theorem. In fact, if you only know one length in these two triangles, you can find the other two using these properties. All right, well, let's do some examples. Find some missing sides and some missing, using our special properties. So here we have a 45, 45, 90. And again, if you remember, the two legs in the 45, 45, 90 are equal. So if that one's 5, the other is 5. And to get to our hypotenuse, it's just 5 times the square root of 2. In fact, the exact example I used earlier. Now what about if I need to go backwards, right? Think about here, we kind of needed to multiply one of these lengths by the square root of 2, right, to get to our missing length. Well, what if I need to go backwards? What if I know the hypotenuse? I could divide by the square root of 2. In fact, you can even think of this 11 root 2 divided by root 2. Those cancel and we get 11. Or you can just use pattern recognition, right? This happened to have the root 2 with it, so that number in front of root 2 is x, or our length of our legs. So once again, of course, another 45, 45, 90. If we divide by root 2, we can find the length of a leg, and our other leg will be equal. Okay, well, we can use this idea to go from a hypotenuse that doesn't have the root 2 with it and still find these missing legs. So again, following our pattern, we know to get to the hypotenuse, we'd multiply by root 2. So to go backwards, let's divide. So if I do 10 divided by root 2, now you might remember we're not supposed to leave radicals in the denominator. And the way we do get rid of that is we multiply top and bottom by root 2. So we get 10 root 2 over 2, which actually simplifies to 5 root 2. The 10 and 2 outside the radical can be reduced. So in fact, this ends up being 5 times the square root of 2, and this leg ends up being exactly the same. Okay, try this out for, say, D. See if you can figure out the length of our other two missing legs here, and unpause the video. Okay, so this one, the fraction can't be reduced, right? 7 halves. But same idea, we divide by root 2, so we put 7 over root 2, and then we rationalize the denominator. We multiply top and bottom by square root of 2, so we get 7 root 2 over 2, and this time the 7 halves does not reduce. So it's just 7 root 2 over 2 for both legs. Okay, let's move on to our 30, 60, 90 properties. So kind of the key here is the shorter leg. So again, this is called the short leg. This is our longer leg. And then we have the hypotenuse, right? So if you know the short leg, it's really fast to get to the other two. Double it to get the hypotenuse, multiply it by root 3 to get the longer leg. So my goal is always to get back to the short leg if that's not what I started with. So for example, E, they did start us with the shortest side, so it should be easy to find the hypotenuse. We double it to find the hypotenuse and multiply it by square root of 3 to find the longer leg. So we're just following those two patterns there. Okay, well, what if this time they started me with the hypotenuse? Well, remember, the relationship between the hypotenuse and shortest leg is that the hypotenuse is twice as big. Again, instead of multiplying by 2 to go this way, we can think of it as dividing by 2 to go the other way. So the shortest leg is 6. We now have the short leg, which is the key. So to find the longer leg, it's the short one, 6, times the square root of 3. Okay, G, you might do sight recognition and recognize that this is a number times the square root of 3, which follows kind of our long leg pattern. And that's fine. Or think of, again, if I knew the short leg, to get to the longer one, we multiply by square root of 3. So if we need to go backwards, we would divide by square root of 3. So 5 root 3 divided by root 3, the root 3's cancel, and we get 5 as our shorter leg. Double it to get the hypotenuse, and our other length is 10. Okay, here's one. It's kind of similar to how we did C and D, but following our pattern for the 30, 60, 90. See if you can figure out H, and then unpause the video. Okay, so for H, if you divide by root 3 and rationalize, multiply top and bottom by root 3, you get 7 root 3 over 3, and that 7/3 does not reduce. To find the hypotenuse, we need to double the shorter leg here. So multiply it by 2, or 2 over 1, and only the 7 on the outside will be the only number that doubles. So we get 14 root 3s over 3.